Welcome to this NPTEL lectures on robotics, basics and advanced concepts. In the last three lectures, we had looked at the kinematics of serial robots. We had looked at the direct kinematics problem and the inverse kinematics problem. In the inverse kinematics problem, we showed that you need to derive a single equation in one of the joint variables, which we can then solve to obtain the joint variable given the position and orientation of the last link or the end effector link. So in this lecture, we will look at this concept of elimination theory and solution of nonlinear equations. So this will help us understand how we can derive in general a single equation in one of the joint variables. So quick review of inverse kinematics of serial robots. The inverse kinematic involves solution of a set of nonlinear transcendental equation. We desire a closed form of our analytical solution over a purely iterative or numerical approach. Okay, and the reason is this closed form solutions provide criteria for the workspace of the robot and how many configurations are possible to reach a given position and orientation. All the multiple configurations which are possible solutions of the inverse kinematics problem. So the general approach for inverse kinematics of serial robots is first convert the transcendental equations to polynomial equations using tangent half angle substitution. Okay. So the kinematics involves sine and cosine thetas, and we can convert that into tan theta by 2, which is denoted by x, and then we get an equation in terms of polynomial in x. Then we need to eliminate sequentially, or if possible in one step, joint variables to arrive at a single polynomial in one joint variable. Okay, and then we solve if possible in closed form. For example, up to quartic equations we can solve in closed form for the unknown joint variable, and then obtain all other joint variables by back substitution. Okay, so the key step is to obtain the univariate polynomial by elimination, and this is what we will see in this lecture. So let's start. What is elimination theory? So the first important concept is if you are given two polynomial equations, let's say f of x comma y equals 0 and g of x comma y equal to 0 of degree m and n. Okay, so the important concept is what is the degree of a polynomial. So the degree of a polynomial is the sum of the exponents of the highest degree term. So for example, if f of xy is xy square plus x square y plus x square plus y square plus 1 equal to 0, the degree of this polynomial is 3 because the sum of the exponents of x and y in the first and second term is 3. Okay. What do we know? If you are trying to eliminate an equation between two such polynomials, there is a very well-known theorem called Bezout's theorem. Okay, so if I have two polynomials f of x comma y equals 0 and g of x comma y equals 0 of degree m and n, there is a maximum of m into n xy values which satisfy both these equations. Okay, the important word is maximum of m into n. This is an upper bound. It includes all the real possible values of x comma y, complex conjugate values of x comma y, and also solutions at infinity. So there is this whole idea that there are some solutions which are at infinity. So for example 1, if I have an equation which is x square plus y square equal to 1, so this is nothing but an equation of a circle. Okay, origin 0, 0 and radius 1. And we have another equation which is y minus x equal to 0. So this is a line passing through the origin at an angle 45 degrees. So we can see that these two equations, x square plus y square equal to 1 and y minus x equal to 0, are satisfied by two sets of values of x and y. So these are nothing but plus minus 1 by root 2 comma 1 by root 2. Example 2, if you have the same circle but the line is now y minus x equals to 2. So now you can see that these two equations do not have any real xy which satisfies these two equations. Okay, there are no real values of x and y possible. Finally, again we look at this circle, and the line is now y minus x equal to square root of 2. So then you can draw and check that it is satisfied by two coincident real values of x comma y. Basically, this line is tangent to this circle, and both the solutions are at one place. Example 1, 2 and 3 can also be interpreted geometrically. So the line y minus x intersects the circle at 2 points, quite obvious. Line y minus x equals to 2 does not intersect the circle at real points, and y minus x equal to square root is tangent to the circle at x square plus y square equal to 1. Okay. You can also verify that if you take two parabolas or two ellipses or two hyperbolas, okay, these are called quadratic curves. Okay, so we have power of x and y as 2. So they can intersect at 4 points. One apparent contradiction is if you have two circles. Okay, so we can sketch two circles on a sheet of paper, and then you can see that it will never intersect at 4 points. The circles are quadratic, but they never intersect at 4 points. So this contradiction can be resolved if homogeneous coordinates x, y, w is used to represent the equation of the circle. Remember, we had this homogeneous transformation matrix where we added a 1 equal to 1. In terms of a generalization of that, we could have added an equation w equals w. Okay, so that's what makes x, y, which are normal coordinates, and if you add another coordinate w, okay, so that is what is called homogeneous coordinates. Okay, so in terms of homogeneous coordinates, you can show that there are two complex conjugate solutions for two circles at infinity for any two circles. Okay, so whatever is the radius of the circle, if you draw two circles, they intersect at 2 points, you can show, and two other points are at infinity. So Bezout's theorem can be extended to two m and n order manifolds. It can be shown that, or it has been shown that they intersect in at most a m into n order submanifold. Okay, so example 1, a sphere which is x square plus y square plus z square equal to 1. Here m is equal to 2, and intersects a plane x equals to 0, okay, at which is n equals 1 in a circle. Okay, this is obvious. If you take a sphere and you cut it by a plane through its origin, you will get a circle which is y square plus z square equal to 1, and this is a second order curve. Okay, so the submanifold is 1 into 2, which is second order. You can also have two cylinders, okay, which is m and n are both 2, and we know from CAD, or we know from our basic geometry, that it intersects in a 4th degree curve. Okay, two cylinders intersect at a 4th degree curve. Bezout's theorem is of no use in obtaining the solution. It is not a constructive theorem. All it is telling you that there are m into n possible x comma y or m into n submanifolds, okay, but it doesn't tell you what are these x comma y points. Okay, so one constructive method is given by Sylvester's. Okay, it is available in this book by Salmon in 1964, but this was developed in the 1800s. It is called the Sylvester's dialectic elimination method, and I want to show this in a little detail. So through an example first. So consider two polynomials x and y in x and y. So f of 1 x comma y is given by a2 y x square, a1 y x, and a0 y. So it is quadratic in x square, but the coefficients could be any functions of y, okay, arbitrary functions of y. So we have these two polynomials, and ai, bi are arbitrary polynomials in y are constant. Okay, so what does the Sylvester's method tell you? it tells you that we generate additional equations by multiplying both these two equations by x. Okay, so if I multiply x into f1, we will get a2 y x cube, a1 y x square, a0 y x plus 0 equal to 0. Similarly, if I multiply the second equation by x, I will get b2 x cube plus b1 x square plus b0 x equal to 0. Okay, so I have generated 4 equations. Okay, the second step in Sylvester's method is very important. It tells you that we consider x cube, x square, x which is x to the power 1 and the constant which is x to the power 0 as linearly independent variables. Okay, so the word linearly is important. They are clearly not independent because the second x square is clearly square of x to the power 1. So once you consider these as linearly independent variables, these 4 equations can be written as a matrix equation which is Sm into y multiplied by x cube, x square, x1 and x to the power 0 square, okay, column vector equal to 0. And I will show you what is Sm next. Okay, so it's basically what you will see is that we will have a2, a1, a0 and 0 in the first row, a2, a1, a0, 0, a2, a1, a0 in the second row and so on. Okay, so the set of 4 linearly independent equations are a2, a1, a0, 0 into some column vector, 0, a2, a1, 0 into some column vector and so on. Okay, b2, b1, b0, 0 into the same column vector and 0, b2, b1, b0 in the same column vector. So this equation, which is of the form ax equals to 0, it's a set of linear equations of ax equal to 0. Okay, so this set of equations have a non-trivial solution when determinant of this Sm is equal to 0. This is from linear algebra. So basically we have determinant of that matrix equal to 0. Okay, so how did I get this matrix? Okay, there's a trick. What you can see is that the second equation is nothing but the original f1 equation. So a2 into x square plus a1 into x plus a0 into x to the power 0 equal to 0. When you multiply this equation by x, you basically shift this row to the left. So similarly, the first equation was f2 was b2 x square plus b1 x plus b0 equal to 0, and we multiplied by x and we shifted to the left. So what we have by multiplication is 4 equations in 4 unknowns. So we have basically a square system of equations, and hence from linear algebra we say that the determinant of that matrix must be equal to 0. In this case, we can find the determinant. It is quite simple. We just use the rules of determinant. It reduces to this expression, which is a2b1 minus b2a1 into a1b0 minus b1a0 minus a2b0 minus b2a0 square equal to 0. Okay, so remember all the a's are constant or functions of y. Okay, so hence determinant of Sm equal to 0 is only a function of y. So what have we done? We have managed to get rid of x. Okay, we have obtained a single equation only in y. Okay, it is important to note that this equations Sm into x cube, x square, x1, they are not strictly independent. Okay, they are linearly independent because we are considering these x cube, x square, x to the power 1 and x to the power 0 as linearly independent variables, but they are actually non-linearly dependent. The variable x can be obtained from the set of linear equations. Okay, so we have Sm into some x cube, x square, x1, z, x to the power 0 equals to 0. We can do row reduction. Okay, so basically multiply the first equation by something, subtract from the second and so on. Okay, standard approach as in linear algebra to solve a set of equations. And what we will get is that the third row will become x to the power 1 into something will be equal to 0, and we can simplify that and see that x to the power 1 is given by minus a1 b0 minus b1 a0 divided by a2 b0 minus b2 a0. It is also equal to a2 b0 minus b2 a0 divided by a1 b2 minus a2 b1. Okay, so the x computed using the two expressions here right hand side must be same and can be used as a programming numerical consistency check. So one thing what you can see is this a1 b0 minus b1 a0, this left term here should be equal to this, which is nothing but if you expand it out you will get determinant of Sm of y equal to 0. So we are not getting any new information or inconsistent information. So we get an x in two ways, both must be same, and we also show that these two terms must be related by determinant of Sm y equal to 0. Okay, so what have we done? We have got a single equation in y and we also have solved for x. So in general, if I am given an mth degree polynomial p of x, which is I equals 0 to m, ai x to the power I equal to 0, and an nth degree polynomial q of x I equal to 0 to n, bi x to the power I equal to 0, where a and b are coefficients, could be functions of y or constants. We construct the Sylvester's matrix of p and q by basically starting with the original equation multiplied by x first, then multiplied by x square and so on till you get some terms top half like this. And similarly you take the b equation q of x, bn x to the power n and so on, b0, then you again multiply by x as many times as possible to eventually get a square matrix. Okay, so we have to multiply by correct number of times the first equation p of x and the m of x such that we get a Sylvester's matrix which is m plus n into m plus n. It's a square matrix. So all the unfilled elements in this matrices are 0. Okay, so as I have said, we are multiplying by x. So the ith row of the top half are the coefficients of px into xi for I equals n minus 1 to 0. And the ith row of the bottom half are the coefficients of qx into qx to the power xi, and I is m minus 1 to 0. So this matrix is m cross n of dimension m cross n into m cross n. And Sylvester's criteria is that the polynomials p of x equal to 0 and q of x equal to 0 have a non-trivial common factor, meaning has a non-trivial solution x if and only if determinant of Sm equal to 0. Okay. So what is the analogy? This is basically an analogy is from linear equations. Okay, so Sylvester's followed this idea of what happens when we have a linear equation, and then he extended it to nonlinear equation, except that the column vector, the unknowns are not really independent. They are x cube, x square, x to the power 1, 0 and so on. Okay, so all powers of x, x to the power m plus n minus 1 and so on, including the constant term, are treated as linearly independent variables. Okay, and this matrix is always of dimension m plus n into m plus n. So in general, whenever determinant of Sm is equal to 0, we will get a non-trivial solution of x to the this vector x to the power m plus n minus 1, x to the power m plus n minus 2 all the way till x to the power 0. Okay. So what is the algorithm? We can write it in steps. So given two polynomials f of x comma y equal to 0 and g of x comma y equal to 0, rewrite these two polynomials as ai x to the power I. So basically take all the y parts in the coefficients and other polynomial variables. So qi as bi function of y to the power x to the power I equal to 0. Okay, so now all the coefficients of these polynomials are functions of y or constant. Then obtain Sm of y exactly in the form as I showed you. You multiply p of x correct number of times with x, q of x correct number of times with x, and then form the square matrix, and then you compute determinant of Sm of y equal to 0. So this is a polynomial in y alone. Okay, so in this two steps we have eliminated x. Okay, that is why it is called theory of elimination. So we solve determinant of Sm of y equal to 0 if possible analytically or numerically. Okay, so as I have discussed last lecture, that if it is up to quartic, then we can solve analytically. Otherwise, you have to do numerically. And once we have y, okay, possible solutions for this y, then this equation 39 can be solved using standard linear algebra techniques, basically row reduction for the linearly independent unknowns x to the power m plus n minus 1 all the way to x to the power 0. Okay. And the integrity of the numerical procedure can be verified by checking that x to the power 1 and say x to the power 2 are related in this form. Okay, x to the power 1 square is nothing but x to the power 2. So as we can see, this Sylvester's matrix Sm is m plus n into m plus n, and determinant of Sm can equal to 0 can become computationally quite expensive. So for example, if m is, let's say, 5 and n is 6, so this is 11 by 11 matrix, and determinant of an 11 by 11 matrix is pretty bad. Okay, so Bezout's, same person as Bezout theorem, in 18th century proposed a method where the determinant of the order max of m and n needs to be computed. We don't need to compute m plus n into m plus n matrix. We need to compute a matrix which is maximum of m and n. So in that example of m5 and n6, we will need to generate a matrix which is 6 by 6 and compute the determinant of that. Okay, so what is the key idea in Bezout's matrix? The key idea is to divide instead of multiplying to get the required number of independent equations and a square matrix. Okay, so previously we were multiplying by x. Now we have to do suitable divisions. Okay, so example. So consider again two polynomials in x and y, same two polynomials, a2 as a function of y x square, a1 yx, and a0 y equal to 0, and b2 x squared plus b1 x plus b0 equal to 0. So we write a2 y x square is equal to minus a1 x minus a0 y. So basically we take these two terms on the other side, and similarly b2 we take these two terms on the other side, and if x is not equal to 0, we can divide those two equations and we can get a2 by b2 is a1x plus a0 divided by b1x plus b0. Okay, we can also take a2x plus a1, and so basically take x common outside, is equal to a0. Okay, and similarly b2x plus by with x common is equal to minus b0, and again divide both of them and we can get another equation in x. Okay, so basically what have we done? By dividing suitably, we have now obtained two equations in x alone. We have managed to get rid of x squared. Okay, and then we can expand these two equations and write in a matrix form. So you can see it will be a2 b1 minus a1 b2 into x, okay, plus a2 b0 minus a0 b2 into x to the power 0. So that will be the first equation. Similarly, the second equation will be a2 b0 minus a0 b2 into x plus a1 b0 minus a0 b1 to the power into x to the power 0 equal to 0. Okay, so for non-trivial x to the power 1 and x to the power 0 treated as independent variables, the determinant of this matrix must be equal to 0. So this is the Bezout's matrix. So we started with two polynomials, second order polynomials, quadratic polynomials, and the Bezout's matrix is 2 by 2. Okay. So can we solve for x? Yes, we can go back and look at any one of these equations and solve for what is x. Okay, so we can show that x is given by minus a1 b0 minus b1 a0 divided by a2 b0 minus b2 a0, or this term. Okay, so the expressions for x are same as from the Sylvester's method, but the Bezout matrix is now 2 by 2. Okay, so what about the determinant of the Bezout's matrix and the determinant of Sylvester's matrix? Both are exactly same. Okay, so they will both give the same expression. So this is an expression only in y. So we have eliminated x, and what we get is some determinant of s of my equal to 0 or determinant of bm my equal to 0. Okay, so although the dimension of Bezout's matrix is less, okay, it's 2 by 2, but each term in the matrix is more complex. Okay, so remember, in the Sylvester's matrix we had the a2, a1, a0, and then we shifted left. Okay, so we had a 4 by 4 matrix with a's and b's. Here you have a 2 by 2 matrix, but each term is complicated. No, it is a2 b1 minus a1 b2 and so on. Okay, so it is not as if we are shifting the equation by left. We have to actually compute the terms. So it is possible to do, but nevertheless it is more complex. So in general, if you are given p of x as a polynomial, ai x to the power I equal to 0, nth degree polynomial, and q of x as an nth degree polynomial, bi x to the power I equal to 0 with m greater than m. So for x not equal to 0, eliminate xm. So previously we had eliminated x square from px and x to the power m minus n qx by rewriting it in this form. am by bm is equal to this. Okay, then you can expand this and we will get an expression in x to the power m minus 1, m minus 2, and all the way to x to the power 0. We can also eliminate x to the power m by writing, as I had said in that previous example, we can write the equations in two different ways. We can take x common and we can get a to the am xm x plus am minus 1 divided by bn x plus bn minus 1 is equal to right side. Okay, and then we can show that we get an equation in x to the power m minus 1 when you expand this out, which will be of the form am minus 2 bn minus 2 am x to the power m minus 1 and so on. And the last term will be a0 bn minus 1. So here it was a0 bn, here it is a0 bn minus 1 plus something else will come. Okay, and we can repeat this to obtain n equations with the nth equation given in this form. So am minus m minus n bn minus am b0 into x to the power m minus 1. Likewise, some term, complicated term with a's and b's to the power x into xm minus 2 and so on. And we can also construct m minus n equations by multiplying qx by x to the power m minus n minus 1. So eventually we have all these equations 45 and 46, and we can form the Bezout's matrix. So the Bezout's matrix consists of the first term is this, then whole bunch of terms, then last equation is am minus n all the way to a0 b1, and since n is greater than m, we have assumed, so we have bn minus 1 all the way to b0 shifted left by some number of times and all the way to b0. The last equation is bn all the way to b0. Okay, so where the unfilled entries are all zeros. So the criteria for non-trivial common factor between the two polynomials, non-trivial x, is determinant of Bm equal to 0. So if m equals to n, then in equations 43 to 45, a set of n linear independent equations, n unknowns are already available. Okay, so we don't have to do these complicated things. So we can solve for the unknowns by standard linear algebra techniques by row reduction. So equivalence of Bm and Sm. So intuitively, the Bezout's matrix and the Sylvester's matrix should be related. Okay, we are starting from the same set of two polynomials. We are solving the same common factors x comma y, or solutions of both the two polynomials. Okay, so they must be related. So I showed you for the two quadratics, determinant of Sm is equal to determinant of Bm. Okay, and we can also show in general that the determinant of Sm and determinant of Bm will be equal for any two polynomials, m and nth order polynomial. So in summary, the Bezout's matrix is obtained by division. Sylvester's matrix was obtained by multiplying each equation. Bezout's matrix is of less dimension, but the terms are more complex in comparison to Sylvester's matrix, and both give the same x and the same eliminant, okay, determinant of Sm of y equal to 0 or determinant of Bm of y equal to 0. Both the expressions are same. Okay, so with this, we now come to the last item in this inverse kinematics of serial robots. So I want to use whatever we have learned of eliminating joint variables, okay, this theory of elimination, whatever we have discussed, to obtain the inverse kinematics of a general 6R robot. Okay, so this is a fairly advanced topic. For a long time, the exact solutions to how to obtain the inverse kinematics of a general 6R robot was not known. Okay, so what is general 6R robot? So general 6R robot means there are no constant DH link parameters of special values. So remember, very often we saw alpha I minus 1 was 0, or AI minus 1 was 0, okay, or DI was 0, or alpha I minus 1 was pi by 2. Okay, so cos pi by 2 will be 0. So there are some special zeros and angles which are 0 or plus minus pi by 2. Okay, so we don't have any of those. Okay, so if you have special values of DH parameters, such as in the case of the Puma 560, the elimination is always much easier. Okay, if there is a prismatic joint, again the elimination is much easier. Okay, because we don't have cos of theta and sine of theta. The prismatic joint variable is d. Okay, so we don't have cosine and sine of d, right? So as I have mentioned, the inverse kinematics of a general 6R robot was unsolved for a long time. Okay, several researchers have worked on the problem. Historically, Duffy and Crane first derived a 32nd order polynomial in one joint variable. So the idea is that you do elimination from a set of equations and obtain a single equation in one of the joint variables, which you can solve numerically if required. So Duffy and Crane in 1980s said that we can derive a 32nd order polynomial in one joint variable. So which means, given a position and orientation of this general robot end effector, okay, we can reach that position and orientation in 32 possible ways, upper bound. Okay, many would be imaginary. Eventually, Raghavan and Roth in 1993 derived a 16-degree polynomial in one joint angle. Okay, so this is what is known, and this is what is agreed, that given a position and orientation of an end effector of a general 6 degree of freedom robot with rotary joints, there are 16 possible solutions, inverse kinematic solutions. And they used extensively this elimination theory, which we just finished. Okay, and I am going to show you the outline of the approach. Okay, it is very complicated. They have written many papers. It is many steps are involved, but just to get a feel that we can solve problems like this now that we have tools from elimination theory, I am going to give you the steps which are used by Raghavan and Roth. So the first important step is that the direct kinematics for a general 6R manipulator is given by this equation. It is standard, okay, by now, that the sixth coordinate system, position and orientation, with respect to the 0th coordinate system is multiplication of 6 linked transformation matrices. And each of these linked transformation matrices, say I minus 1, is a function of only one joint variable theta I and 3 constant dh parameters. This we know. Okay, so what is the inverse kinematics problem? The left hand side is given and we need to find the 6 joint variables in each of these transformation matrices. Okay, so in each of theta I. So step 1, first write I minus 1 IT, the link transformation matrix, as a product of 2 matrices. Okay, so this is Raghavan and Roth's approach. What is the 2 matrices? One is something which is dependent on only the constant dh parameters, which is called as ST or structural part, and then another part which is I minus 1 IT, which is the joint part. Okay, can we do this? Yes. So for example, I minus 1 IT, the structural part into joint parts. The structural part looks like this: 1 0 0 AI minus 1 0 cosine alpha I minus 1 minus sine alpha I minus 1 and so on. And the joint part is cos theta I minus sine theta I and so on. Okay, and di. So this second matrix contains the joint variables theta or d, and the first matrix contains the twist angle and the link length. Okay, so this you can see is constant, whereas this is a function of joint variable theta for rotary joint, and if it was a prismatic joint, then you will have d. So that is step 1. Step 2, we reorganize the equation of direct kinematics, rewrite it as 2 3 t joint, then 3 4 4 5, and then 5 6 t joint. So, and this is equal to 2 3 t structure to the inverse, then 1 2 inverse, 0 1 inverse, 0 6 t, and 5 6 t minus 1. This is the same as the direct kinematics equation. So if you think a little bit about it, we have broken some of the matrices into the structural part and the joint part and then rearranged. So it turns out that the LHS is only a function of 3, 4, and 5. So theta 3, theta 4, and theta 5. Okay, whereas the right hand side is a function of theta 1, theta 2, and theta 6. Okay, so this is a link transformation matrix equation. Okay, so there are 6 scalar equations or 6 independent scalar equations in this matrix equation. Remember, the last row is 0 0 0 1, so there is nothing in it. So out of the top 3 by 3 and the last 3 by 1 column, we can only get 3 plus 3, 6 independent equations. Okay, and these 6 scalar equations are obtained by equating the top 3 elements of column 3rd, okay, the position, okay, and 4 on both sides of the equation 50. Okay, so they do not contain theta 6. So we can rewrite as A into S4 S5, S4 C5, C4 S5, and so on into 1 is equal to B into S1 S2, S1 C2, and so on. So we have managed to look at these equations and pick the ones which do not contain theta 6. Okay, so A is a 6 by 9 matrix with elements linear in sine theta 3, cos theta 3, and 1. This is also important. So in this matrix A, theta 3 is there, but they are containing only sine theta 3, cos theta 3, and 1. There is no square and product terms. And in B matrix, it's a 6 by 8 matrix of constants. Okay, so we denote the columns 3 and 4 by P and L. Okay, so now we come to the elimination. So we eliminate 4 of the 5 variables, theta 1, 2, 3, 4 and 5. So in this set there is theta 1, 2, 3, 4 and 5. Theta 6 is not there. And how do we do that? This is the contribution of Raghavan and Roth in 93. We obtain a minimal set of 14 equations, 3 equations from P, equating P from both sides, 3 equations from L, 1 scalar equations which is the dot product of P dot P, 1 scalar equations from the scalar dot product P dot L, 3 equations from P cross L, and 3 scalar equations from this vector equation P dot L minus 2P dot L into P. Okay, so you can see 3 plus 3 6 plus 2 8 plus 6 14 equations they obtained from that matrix equation. Okay, so this 14 equations can be written as P into S4 S5 S4 C5 and so on. So theta 4 and 5 is equal to Q into this. So this P matrix is a 14 by 9 matrix containing sine theta 3, cos theta 3 and 1, and Q is a matrix of 40 constants. So we eliminate 4 theta I in 1 steps. And how do we do? First use any 8 of the 14 equations in equation 52 previously. Any of this from this equation, we use any 8 of the 14 equation and solve for the 8 variables, independent variables, quote unquote independent, S1, S2, S1, C2, C1, S2, C1, C2, S1, C1, S2, C2. Okay, so these are 8 linear equations in 8 unknowns. We can always solve for them. Okay, substitute the 8 variables in the rest of the 6 equations to get R, which is now a new matrix with this function of sine theta 4, sine theta 5, S4, C5 and so on to 1. Okay, so R is a 6 by 9 matrix whose elements are linear in sine theta 3 and cosine theta 3. They do not have any square terms in sine theta 3 and cosine theta 3. We eliminate theta 4 and theta 5. We first use tangent half angles formulas for sine theta 3, cos theta 3, sine theta 4, cos theta 4, sine theta 5, cos theta 5. On simplification, we can write some matrix S into x4 square. What is this x4? That is tan theta 4 divided by 2. What is x5? It is tan theta 5 divided by 2. So we have converted the trigonometric functions sine and cosine of theta 4 and 5 into polynomials. So we are going to eliminate theta 4 and theta 5 in 1 step. Okay, so we get this equation and we eliminate x4 and x5 using the Sylvester's dialectic method. So basically we have some matrix which is 6 by 9 into 9 by 1 equal to 0. So we pre-shift the rows, we multiply some equations by x and so on. Okay, so we generate 3 additional independent variables when you multiply it by x4 and x5 in some particular way. So we get x4 cube, x5 square, x4 cube, x5 and x4 cube. So we get a system of 12 equations in 12 unknowns. Okay, so these 12 equations in 12 unknowns can be written as S, 0, 0S. So basically they are being shifted to the left when you multiply. And we have this original 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 variables in x4 square, x5 square and so on. But then we have multiplied and we have generated additional variables x4 cube, x5 square and so on. So we have the form of Sm into some y vector or x vector sm of y into x vector is equal to 0. So following Sylvester's method, we set this determinant is equal to 0 because that is the condition such that this column vector is non-trivial. Okay, so what do we have? We have determinant of S, which is some horribly complicated terms, which contains only theta 3, okay, and so on, okay, sine theta 3 and cos theta 3. So we have expression, long expression, which on simplification will give us 16th degree polynomial in tan theta 3 by 2. Okay. So if you do the algebra, if you do the simplification, you will actually get a 24th degree polynomial in x3, but there are these common factors which is 1 plus x3 squared to the power 4, which can be removed. Okay, this can never be 0. So we can solve this 16th degree polynomial to obtain theta 3. Okay, so theta 3 is 2 into tan inverse of x3, which we get. So how do we solve this 16th degree polynomial? We have to do it numerically. So once theta 3 is known, we can find x4 and x5 from this equation, okay, simply by row reduction. So we can find out what is x5 and what is x4, these two elements here, just like we found out what is x after doing elimination. So once we find x4 and x5, we find theta 4 and theta 5 by 2 into tan inverse of x4 and x5. Once theta 3, theta 4, theta 5 are known, we can go back and solve the right hand side. Remember, the right hand side does theta 1, theta 2 in one set of equations in 52, and we can obtain unique theta 1 and theta 2. Finally, to obtain theta 6, we go back to the original set of equation, which is 5, 6t, can be now written as 4, 5 inverse, 3, 4 inverse, 2, 3 inverse, 1, 2 inverse, 0, 1 inverse into 0, 6. So this is given to us, and each of these are functions of theta 4, theta 3, theta 2, theta 1, and so on. So we can solve for theta 6 from this equation. Okay, so are known, and from the 1, 1 and 2, 1 elements gives two equations in theta, sine theta 6 and c6, and we can get a unique value of theta 6. Okay, so this is the basic algorithm. So important thing is that we obtain the 16th degree polynomial in x3 from this step. So this is the most important step, how to obtain this matrix S0, 0, S into this long column vector with 12 variables, okay, in terms of tan theta 4 by 2 and tan theta 5 by 2 and their powers. Okay, so once we know this, we find that the whatever is in this matrix is only function of theta 3, so hence we can obtain theta 3. Okay, so once you obtain theta 3, then we find theta 4 and 5. Then once theta 3, 4 and 5 are known, we obtain theta 1 and theta 2, and then finally once all the angles are known, we find theta 6. Okay, so what is the summary? Any general 6R robot, okay, has 16 possible solutions. Okay, why? Because the polynomial in theta 3 was 16th degree. If you have special geometry, meaning certain link lengths are 0 or some angles are 90 degrees or 0, this polynomial in x3 can be of lower order. Okay. If one or more joints are prismatic, ik is much simpler. Okay, since the prismatic joint variable is not in terms of sines or cosines. There is no general expression for workspace boundary. Why? Because we do not have closed form analytic solutions for the 16th degree polynomial. We can only obtain the solutions of this 16th degree polynomial numerically. So how do I find the workspace? If all the roots of the 16-degree polynomials are complex, then this position and orientation is not in the workspace of the manipulator. Okay, so this is an important concept. So I have given you a 16-degree polynomial. I go to MATLAB and find the solution of this 16-degree polynomial and see that all the roots are complex conjugates. So then the point from which I got the 16-degree polynomial is outside the workspace. All the inverse kinematic solutions and entire workspace may not be available due to joint limits and limitations of hardware. This is also a very important concept. Okay. So till now, we have not assumed that there are joint limits. So in an actual robot, okay, you cannot move the joint beyond certain limits. So if you want to consider the joint limits, then the workspace is further reduced. So with this, we will stop this lecture. So in this lecture, I showed you a way to eliminate from two polynomials, f of xy equal to 0 and g of xy equal to 0, first x, and then solve for y, and then ultimately solve for x again. Okay. And then I showed you that we can use this Sylvester's method or Sylvester's matrix, this idea behind eliminating and then finding the solutions for x and y, okay, in solving the general inverse kinematics of the general 6R robot. Okay, so with this we'll stop.